Yeah. Okay, so we're doing percent composition. So it's the percent by mass due to each element. Okay? It says there's two forms this can take, but really the general form, so your percent comp is just the part over the whole thing times 100. That's it. It's the part over the whole times 100. So like if you had, if I gave you a quiz that was out of 30 points and you got a 28 on the quiz, you didn't fail it, did you? No, no, you didn't fail it. So if you got a 28, if your quiz was worth 30 points, if you got a 28, right? Oh, yeah. So then you would do, okay, well, so 28 divided by 30, the part over the whole thing, what it's worth, times 100. And no, you got an A, you did great, right? Okay, so that's all percent composition is. It's the part over the whole times 100. That's literally all you're doing every single time. You have to do it in terms of mass, so you have to use grams, which means you have to use the periodic table. Okay, so there is, I mean, this formula, it's the same thing that I just wrote, right? Percent is equal to the number of atoms, in the formula times the atomic mass times 100 over the whole thing, the molar mass of the whole compound, okay? So the part would be the number of atoms in the formula times the atomic mass. The whole would be the molar mass, and then you multiply the whole thing by 100. So first example, it says find the percent composition of sodium carbonate, okay? So first of all, we have to figure out what is the formula for sodium carbonate, right? So what's the formula for sodium carbonate? Na2CO3, yeah, because carbonate's -2 and sodium's +1. All right, so real quick, on your own, in your calculator, calculate the molar mass of that real quick. I'm going to do it on mine as well. Okay, so that's the molar mass. Now, to make things just a little more simplified in our calculator, I want you to real quick just hit the store button and then letter X, which is right next to the alpha button, and we're going to temporarily store, and then hit enter. And we're going to temporarily store that number as letter X in our calculator. It'll just make things go a little quicker when we start sticking these in our calculator. Okay? All right, so you have 3 parts to sodium carbonate. You have sodium, carbon, and oxygen. So first we want to find for sodium. So for sodium, how many atoms of sodium do you have?
1.
No, 2. There we go. So you do 2 times sodium's mass, which is 22.99, times 100, over the molar mass of the whole thing, 105.99. Okay? So when you stick that in your calculator, I can get it to not glare. There we go. All right, 2 times 22.99 times 100 divided by, and I'm just going to divide by X instead of typing in 105.99. Now, because you use numbers off the periodic table, which is a table of constants, you're just going to round your answer to 2 places past the decimal, just like the numbers in your periodic table were. So that'd be 43.38%. That's it. That's for sodium. Now we have to do the same thing for carbon, because there's 2 more parts, right? So carbon, right? You only have one of them. You don't have to write 1 times the mass. You could just say the mass, right? So the mass of carbon is 12.01 times 100, because you only have 1, so multiply by 100, over the molar mass of the whole thing, 105.99. So then it will be 12.01 times 100 divided by X in your calculator. And again, you want to round that to 2 places past the decimal. So that would be 11.33%. So that's the percent of carbon. Now, you can only have 100% of a whole thing. So to find the leftovers, which is oxygen, you can do the process that you've been doing. So you could do like 3 times 16 times 100 over the whole thing. Or since it is the leftovers and you can only have 100% of a whole thing, you could just do 100 minus the others that you already found. Okay. That's it. That's percent composition, the whole thing. It's easy, right? Okay, cool. The other way to do it is if we give you actual numbers in the problem. Now, if we give you actual numbers in the problem, that's considered data, so you have to use your sig fig rules to calculate. There's no sig figs if you just use the periodic table because it's a table of constants. You just round everything 2 places past the decimal and move on with your life. If you have data, you have to do sig fig rules. Okay? So let's look at example 16. It's still the same format. It's still the same thing that we were doing, the part over the whole times 100. It's the same thing, okay? All right, so you have some unknown hydrocarbon. You have 50 grams of it total, and it has 41.33 grams of carbon, and the rest of it is hydrogen, and we want the percent comp. All right, so first we're going to do carbon. It only has carbon and hydrogen in it because that's all they mention, okay? And I also know that because 41.33 plus 8.67 equals 50. 50 is the whole thing, so. All right, so the part that's carbon, right, so that's the 41.33 times 100 over the whole thing, which is 50.0. Now, you were given in the problem some actual numbers. So now we have to do our sig figs. So how many sig figs are in 41.33? 4. How many are in 50.0? 3. So which one wins if we're doing division? It's the one with the lowest number, right? Okay, so which one wins, 4 or 3? 3. So your answer should have 3 sig figs. So then stick it in your calculator. So what is that to 3 sig figs? 82.6. Okay. Okay. And the rest is hydrogen, so you could just subtract 82.7 from 100, exactly. But you still need to label which is which, so keep it organized. You can do that in your head, right? When you do subtraction rules, it's by the least number of decimal places, but 100 is kind of arbitrary here because it's what your percents should add up to, so it's kind of like a constant, so you can't use that for sig figs. Your number that you are using is 1 place past the decimal, so your answer must be 1 place past the decimal. Okay? All right, when you do hydrates, hydrates are a little easier. You don't do each individual element. You just do the ionic compound portion and the water. That's all you want to know the percents of. So it actually is a little easier. And remember, I told you to memorize the molar mass of water. So that'll help. That'll come in handy here. All right, so it says, for an example 17, what is the percent composition for barium iodide dihydrate? So what's the formula for barium iodide dihydrate? Barium. What indeed is barium? Ba, okay, and then I2 dot, what is dihydrate? 2H2O. Okay, so the first thing you have to do is find the molar mass of the whole thing. So do that real quick on your own. Okay, and this is where knowing the molar mass of water will come in handy.
What is the molar mass of water?
Molar mass of water is 18.02 grams per mole. Yeah, I'll write it at the top up here.
What, Jimmy told us. I don't remember.
So that's the molar mass of water. You need to memorize it. All right, so I get 427.19 grams per mole. for barium iodide dihydrate. Okay, so you know the molar mass of water. So you don't really know the molar mass of just barium iodide all by itself. So I would find the percent of water first, and then the leftovers is just the barium iodide. That way you're pressing less buttons in the calculator, and you can go a little faster if you're going from something from memory. So for water, oops, I meant to put a colon there, sorry. Okay, so for water, you have 2 of them. So it's 2 times water's molar mass times 100 over the whole thing. And you weren't given any numbers in the problem, so what do all your answers need to have in terms of decimal places? 2. Okay, so if that's water, then the rest must be barium iodide. So barium iodide becomes very easy. Okay, I'm having problems with colons now. There we go. 100 minus 8.44. And again, you could probably do that in your head instead of using the calculator, right? Okay. Oops. All right. So that's all percent composition. That's all page 7 and 8 of your homework. All of it. Okay? It's kind of easy. Shouldn't take you more than about 15 or 20 minutes to just do page 7 and 8. The next part of your homework, page 9, is all about empirical formula. So the empirical formula is the simplest whole number ratio of elements in a chemical formula. Okay? So if you had, like look at barium iodide, right? It's BaI2. So the ratio there is 1 barium to every 2 iodides, right? So the ratio is 1 to 2. So empirical formula, the process of doing it, is how you find formulas. Okay? So that's why, like, all of your homework, it's formulas. There's no math. But there's lots of math, so it's very deceptive. Okay. So you have 3 steps to doing this. They're kind of long, okay? So your first step is you begin with the mass of each element, okay? So if you have percentages, you assume that the sample is 100 grams, so each of your percentages is expressed as grams, okay? Okay, then it says the next part, you find the number of moles of each element. So how do you do that? You divide each mass or percentage by its atomic mass of that element, and then that will give you the moles. Okay? Then you look at each of those numbers for moles and you decide which one is the smallest number, and you divide each one of your moles that you just found by the smallest number of moles, because you're trying to find a mole ratio. That's what that 1 to 2 in barium iodide is. That's a mole ratio. So divide all the number of moles by the smallest number of moles. All right. So then it says if the resulting numbers are all integers, those are the subscripts. Okay. So if you get integers, those are the subscripts. Okay. If the number includes a decimal, then you will have to multiply through to get rid of any fractions. Okay. So what are your fractions going to look like? So if you had like if your fraction ended, okay, so let's say if your number is less than 0.25 at the end, or greater than 0.75, then you're just going to round. If your number ends in 0.25 or 0.75, then I want you to multiply by 4. But you don't just multiply the one that ends with 0.25 or 0.75 by 4. You multiply all of them by 4. not just the one. All of them. You'll see in a minute. If it ends with 0.33 or 0.67, okay, so that's like a third or 2/3, right? You're going to multiply everything by 3. And if it ends with 0.5, you're going to multiply everything by 2. Okay, so that doesn't make a whole lot of sense. So we're going to jump right in with both feet. Now there is an example at the bottom of this page. It's in this weird like table with units and stuff. I'm gonna not do a table. So let's skip to the next example. The numbered example should be 18. All right. All right, so number 18 says, find the empirical formula for a substance that has this % composition. All right, so I've got potassium. So I've got 56.6%. Remember I said we're going to assume all percents are grams. So this is how many grams I have of each of these. So I have potassium, carbon, and oxygen. So I'm going to take each of these grams, and I'm going to divide them by the molar mass of that substance. So what's the molar mass of potassium?
39.1.
Uh-huh. What's the molar mass of carbon?
12.01.
What's the molar mass of oxygen? Okay. So then I'm going to stick in my calculator. So 56.6 divided by 39.1, and I get a number. Now, I don't want you to round much for these, okay? So when I write these numbers down, I go at least 3 non-zero numbers past the decimal. So when I write this number down, because there's not really sig figs with this, but I want accurate information. So I'm going to write 1.448 and underline it. So then you do the same thing with carbon, right? So you stick that in your calculator. All right, and you want to go 3 non-zero numbers past. So I get 0.723 and underline it. Okay, and so for this one, I get 2.169 and underline it. Okay, so then you look at each of these numbers that you've underlined. Those are the numbers of moles. Which one has the least amount, potassium, carbon, or oxygen? Carbon. So we're going to divide them all by carbon's number of moles. So we're going to divide them all by 0.723. Okay, so obviously carbon is 1. And when you put 1.448 divided by 0.723 in the calculator, you get like 2.003066, I don't know, something like that, right? That's really, really close to 2, so we're just going to call it 2. And then 2.169 divided by 0.723, you should get exactly 3. You should get an actual integer out of that one. Those are the subscripts on your formula. So the formula is K2C1, but we don't write a 1, O3. That's the formula. That's the answer. Yes?
How did you get like the 1.44 to 0.23?
I did 56.6 divided by 39.1, and that got me 1.448. So I'm kind of going vertically. So then 8.68 divided by 12.01 gives me that. And then 34.7 divided by 16 gives me that. Okay? Let me pause it. Okay, so when you do hydrates, okay, you don't need to do like each individual element. You only need to do the anhydrous part and the water, okay? Because generally what you're looking for will give you the name of the anhydrate, the ionic portion of the compound, and you know it has water in it, so you're looking for how many water molecules it has, okay? So we're going to do example 21. So it says hydrated magnesium sulfate, and they even give you the formula right there, right? I would never do that on a test, but whatever. It has a mass of this, okay? So the hydrate, which means it's this with water attached to it, this is the mass. Okay, then it says this sample is then heated until no water remains. So we're driving off the water. So then the dry magnesium sulfate anhydrate means dry without water, okay, has a mass of this. We need to find the formula and name. All right, so first we do 13.52 grams, right? Minus the anhydrate, right? So minus the magnesium sulfate, right? So minus 6.60 grams. And that will equal what the water is that we drove off, right? So the water that we got rid of, which is what?
6.92.
Yeah. Grams. So then we're going to do this. 6.60 divided by the molar mass of magnesium sulfate. So find the molar mass of magnesium sulfate first. And then you know the molar mass of water. I hope you do. So you divide each one of those by their molar masses to find the number of moles. The number of moles of water is always going to be greater than or equal to the number of moles of anhydrate. So you're always going to divide by the number of moles of anhydrate when you're doing this hydrate business, okay? So you divide by the lower number, which is always the anhydrate, the ionic portion. So that, the anhydrous portion will always equal 1. It has to. It's impossible for it not to. It has to equal 1. So then you just have to figure out the other portion. And it should be an integer every single time. All right, so now I know that my formula is MgSO4 dot 7 H2Os. So that's the formula. And then what's the name?
Magnesium sulfate.
There we go. Magnesium sulfate, heptahydrate. Because it asks for the formula and the name. Okay.
What happens if you find like a decimal in your integer? Like it's like 1.99.
That's close enough to 2 to call it 2.
Just call it.
Yeah.
What if it's like
Okay.
the same where it's like 1.1111?
It's close enough to 1 to call it 1.
Okay.
Yeah.
Less than 0.25.
If the number after the decimal like is 0.2 or less, you round it down. If the number after the decimal is like 0.8 or higher, round it up every single time.
And if it's like 1.3, then you did something wrong.
Then you have to multiply it by 3 because that's a fraction.
Oh, that's what it
Yeah. So we're about to do that. We're about to do the fraction ones. All right. So let's look at number 22. All right. So number 22 says you have an ionic composition that. Yeah. So you divide by each of the molar masses. And then divide by the least number. you should end up with 1.5 leads, 1 phosphorus, and 4 oxygens. But because you have a 1.5 there after the lead, you have to multiply everything by 2. Not just the lead, everything. So this would be times 2, which gives you 3. You'd multiply that by 2, which gives you 2. Multiply that by 2, which gives you 8. So then you'd end up with PB, P2O, or PB, what, 3? Sorry. P2O8. Okay. Does that look right for an ionic compound? Do you know of a polyatomic ion that has 2 phosphoruses and 8 oxygens in it? Do you know of one that has 1 phosphorus and 4 oxygens in it? Phosphate. So what you'd want to do is call this PB3, reduce the 2 and the 8 to 1 and 4, so that's PO4. And the factor that you reduce them by, you put that outside the parentheses, and that's the empirical formula. Compounds are, kooky like that. Okay? Then you can do number 23 on your own.
Oh, I'm tired.